This tutorial calculates the geometry of an excited state. Let's do the water molecule. Let's just take an oxygen, and by the model builder we have a water molecule. Let's use, for simplicity, a semi-empirical method. Choose INDO for no particular good reason. If we do a single point in INDO, we'll see that there's actually 4 occupied orbitals here and 2 unoccupied. No degeneracies or anything like that. And so if we're going to do excited states, we're going to excite electrons from these occupied orbitals to these unoccupied orbitals. To do so, we ask to do a configuration interaction calculation, and we choose singly excited CI, and we're going to take all the orbitals. We could take a subset of the occupied and unoccupied orbitals for the CI, but in this case we're going to take them all. And so we just go ahead and do a single point calculation with CI turned on. It does the calculation, does CI, and computes the electronic spectrum. This is the excited states of water at this simple little basis set with INDO. The lowest excited state, well, at the top here are all the states no matter what, singlets and triplets, and down here these are the states with their intensities, and of course only the singlets have any intensity and not all the singlets have. This is the most intense transition here, but the lowest transition is a triplet excited state of water. So what we're going to do is look at the geometry of that triplet state. So what we're going to do is we're going to optimize, do a geometry optimization, and now since we have turned on CI, the only optimizer we have is the conjugate directions optimizer, which has no gradients and uses only the energy. It's a much less effective optimizer. Not having the gradients gives it lots of limitations. It has to iterate for a long time with the energy to sort of get settled down, and it never quite knows where it is because it doesn't have the gradients to fall back on. But nevertheless, we're going to use it. When we use that, we can optimize an excited state, we can optimize the ground state. Of course, if we're going to optimize the ground state, we would use a better optimizer, or we could optimize MP2 for ab initio. But anyway, we're going to take 0 as the ground state here, 1 is the first excited state, and we're going to optimize that state. So we go ahead and optimize this. It turns out that what we'll find is that this excited state is actually linear. It's going to take us a little bit of time here to get to that point, but as you can see, it is widening the angle very extensively. And what it's going to find is an excited state that is a linear molecule instead of bent the way water is bent in the ground state. So this should be pretty well finished now. What we find is a linear molecule with a bond length of something like 1.08 angstroms as opposed to 0.96 or something like that in the ground state. So it's a little longer bond length in the excited state, and it's linear. So this is the way that one finds the geometry of an excited state.